Good morning, everyone, from rainy Barcelona city, and welcome to this webinar promoted by COLLABAT cluster in methodologies for testing and validation of cells, modules, and battery packs for electric vehicles. My name is Edward Piqueras. I am Research and Innovation Program Manager at EuroCAD Technology Center and coordinator of MARBEL project, an European collaborative research and innovation project for the manufacturing of next generation of battery packs for automotive market. During today's webinar, different speakers will present the latest developments and innovations beyond the state of the art in battery testing. So we will talk about testing for characterizing and getting more knowledge on aging, performance, safety testing cell, testing for digital twin parameterizations, to pioneering cell testing activities and modeling approaches in this sector. As you see, we will start with a brief introduction of COLLABAT cluster and the MARBEL project, so you understand the context of this webinar and where the different researchers and people talking about this topic today, where they are coming from. And after this, we will have different presentations from different topics related to testing. And the event will conclude with a panel discussion, on covering common insights and lessons learned across the different projects. And we will give also some space at the end of the webinar to the audience to pose the questions you have on this topic, exchange some ideas, concepts, and discuss on the main topics, main challenges that this testing of modules and battery packs have. Well, to continue with the agenda, I will start talking about the COLLABAT. COLLABAT is a cluster of 4 projects that were funded under the call LCBAT 10-2020 for the next generation and realization of battery packs for electric vehicles. This call is a funding call under the Horizon 2020 European Research and Innovation Funding Program. So a program funded by the European Commission, and the main goal of this topic was to fund projects that help to accelerate the mass market take-up of battery electric vehicles. By means of increasing the energy density of the battery packs, shortening charging times through high-power charging strategies, enabling traveling over longer distances. This will make to facilitate the adoption of the electric vehicles. The expected impacts of the call were to reduce the battery system weight by 20%, reduce shorter 25% the charging time, extend the useful battery life up to 300,000 kilometers in real driving, and also reduce the environmental impact with a minimum 20% of life cycle energy improvement compared to existing battery packs. So there were also intention to gain knowledge, improve the knowledge at European level on module and pack sensorization and thermal management to achieve these goals, of shorter recharging time and extension of useful battery life. Within this call, there were 4 projects funded by the European Commission, and these projects get together into this COLLABAT cluster, to exchange learnings, best practices, discuss challenges, and also team up for disseminating the results and advances on the 4 projects. The projects are HELIOS, the high performance modular battery packs for sustainable urban electromobility services. Some of the key innovations of these projects concern the hybrid combination of high energy with high power cells, modular and scalable designs, advanced BMS, multi-sensor unit using wireless communication to communicate the sensors with the BMS, Also, they are working with digital twins, IoT cloud-based solutions, fleet management softwares, ultra-fast charging as part of the impacts of the topic is requiring. And they are validating their battery pack in a small city electric vehicle car, okay, and a full-size Bosan Kaya electrical bus, okay. The next project is the one that I have the honor to coordinate in Eurecat is MARBEL, okay, the manufacturing, it is the title on manufacturing assembly of modular and reusable electric vehicle battery for environmental friendly and lightweight mobility. Okay, our project is it's focused on the versatility of different concepts related to the circular economy principles. So we are targeting a design for easy and safety assembly, automatization, the reparability, and easy and facilitating the second life transition of the modules and the battery pack. For this, we are working with advances in the battery management system. We are also tackling the lightweighting of the battery case, using recycled aluminum alloys, and also the topics related with the extension of the life of the battery and the ultra-fast charging strategies by enhancing the thermal management. Related to testing, you will see later, our colleague Daniel will introduce more details. Then we have ALBATROSS, Advanced Lightweight Battery Systems optimized for fast charging, safety, and second life applications. So they are targeting this weight reduction, shortening the recharging time, enhancing the useful battery life, the life cycle improvement, sensorization and thermal management knowledge, and they are validating this on a BMW i3. Finally, Liberty, lightweight battery systems for extended range of improved safety. They are working on a cell-to-pack solution. They work with immersion cooling for thermal management. And they are also working on enhancing the safety system, advanced BMS, and they are validating their battery pack on a Mercedes EQC. Okay, COLLABAT. As you see, we get together these 4 projects, okay, to discuss, engage on technical topics, to discuss and identify potential synergies among the projects. That means identifying common bottlenecks, challenges, and exchanging best practices to overcome them. So to get the best value of money of the funding get from the European Commission, getting together to get more extended results. We structure it in 4 subclusters: sustainability. That you will see later. There is a webinar also planned on next week on 5th December, Tuesday 5th December. And subcluster B on testing. This is the one that concerns to this webinar, that is led by Technische Hochschule Ingolstadt, Charisma Institute, that is leading the testing activities in MARBEL project. Another subcluster on BMS and another one in modeling. Okay, we expect to provide specific outcomes valuable to upcoming European projects, academia, and industry. Okay, that's why we are doing these webinars. And our advances will be showcased on dissemination events. Okay. The subcluster on testing, you will see in this panel discussion later. We have been discussing state-of-the-art test procedures, main drawbacks, problems, exchange different experiences, create lesson learned. This is what will happen during today and in the discussion later on. As I advanced you before, there is another webinar on COLLABAT related to life cycle assessment, the value of life cycle assessment and circular economy, and the influence in the battery industry. You can join us next week, Tuesday, 5th December, from 9 to 11. You can register in looking at our web pages or COLLABAT. Okay. Then, just to finish, some words about MARBEL. I already introduced you. MARBEL, the project that's coordinated by Eurecat Technology Center, and myself, with the help of many other people from Eurecat and the partners of the project, is a 3.5 years duration. So this last year will be the last year on testing our modules and battery packs, okay, and getting final results. We are 16 partners from 7 different European countries. You will see here different research institutes like Eurecat, IREC, the university in Ingolstadt, but also some tier ones, some important tier ones like FICOSA, BTS, OTC, research institutes like SINTEF for the welding. And we are working with Stellantis groups here, Fiat Research Center, and also different industries, tier ones like Agrati, Institute like Fraunhofer, etc. Our main goals are similar to the call, weight reduction, charging reduction, and as I introduced you previously, we are very focused on the circular economy principles to facilitate the easy assembly, disassembly, easy and safe disassembly for an easy transition to second life applications. Okay. And we aim also to provide a design that is adaptable to any kind of cells and vehicles. Well, any question about this project, I will be very happy to answer you. Anyway, you can find us in the web page and follow us in LinkedIn and newsletters, etc. Okay, so let's move to the different presentations today. Okay. I would suggest then, I will stop sharing my screen. Yeah. And yes, I would suggest to start with Liberty, with Christophe Breitfuss from Virtual Vehicle Research and Nick de Beer from Flanders Market. Christophe Breitfuss received his PhD in mechanical engineering from University of Technology in Graz in Austria. Since 2017, he works as a lead researcher in the field of battery crash safety and virtual vehicles, bringing his 10 years of experience in macro meson mechanical battery simulation testing and virtual short circuit prediction. So in Liberty, he is leading the work package for test procedures for safety performance. Okay, he will be presenting part of this presentation, and the other speaker in this part will be Nick de Beer from Flanders Make. He's graduated as Master of Science in Mechanical Engineering with a specialization in vehicle technology. Within Flanders Make, he worked as a researcher engineering on hybrid and electric vehicles and as a test engineer on high voltage batteries and electric motors. He leads the work package in Liberty project for integration testing and concept validation on cell stack and battery system. Okay, welcome Christophe and Nick. Nice to have you here, and I give you the floor to keep going with this presentation. Okay.
Thank you, Eduard, for this nice introduction. So in the next minutes, we will present you aging, performance and safety, developed test procedures, gained test results, and the way of reporting them in Liberty. To the agenda, I will, it's not working. Now, to the agenda, I will start with a short overview on the Liberty project. Then I will talk about safety testing, and then Nick will take over and he will talk about aging and performance testing. So the Liberty project, the full name is Lightweight Battery System for Extended Range and Improved Safety. The overall target is upgrading an electric vehicle's battery in terms of performance, safety, lifetime, and sustainability. 16 partners are involved from 7 countries. We started with the year 2021, and the project lasts 42 months. Objectives are to achieve a range of 500 kilometers on a fully charged battery pack, to achieve a short charging time, 18 minutes instead of 40 minutes from 10 to 80% SOC, to achieve an ultimately safe battery system, to achieve a long battery lifetime from 500 to 1,000 circles down to 80% depth of discharge, or in mileage from 160,000 kilometers to more than 300,000 kilometers. And finally, to achieve sustainability over the battery pack's entire life cycle. Now we come to safety testing. So in Liberty, we want to enlarge the view on safety testing. So for example, a normal situation for a vehicle's battery has thermal loads and mechanical loads which are absolutely non-critical. Then suddenly we have a mechanical event in form of a crash, and we have high mechanical loading, which is very short period, so we can neglect the change of temperature here in this time. And then we have the event of cooling or eventual cooling and influence of cooling. This could be no influence of the cooling or no working cooling anymore due to the crash, or we have cooling which works but or at least reduces the heat inside the battery, or we have optimal cooling which leads to no heat exchange. This leads to 3 different thermal consequences. We could have the worst, which is a thermal runaway over the entire back of the over the entire pack, or we have single cells in thermal runaway and no thermal runaway propagation to other cells which are not influenced by mechanical loading, and or which would be the optimum is absolutely no thermal runaway and nothing happens. Current safety test procedures have the focus here, so on the mechanical loading and then maybe a little bit of cooling. We want to, or we enlarging that in Liberty, we want to take into account the preconditions from normal operation before. Temperature is a very important parameter on the onset of thermal runaway. And we want to take into account the cooling measures. What are they able to avoid? Are they able to avoid thermal runaway propagation, or even thermal runaway of single cells? For achieving this, we have a hybrid approach, which is a combination between testing and simulation. Testing is subdivided into 2 different parts in mechanical testing and thermal runaway testing, and simulation we do only in mechanical matters. On cell level, we have everything. So we have our tests, mechanical tests, thermal runaway tests, and we can make our mechanical model out of the mechanical tests. Same for stack level, we have everything. On back level, we have to do a upscaling approach. That means we cannot test a back, we only have one due to resources and costs. So we are doing this upscaling here virtually and have to estimate the reaction of the whole battery pack. Now we come to cell testing. Concerning mechanical cell testing, we did quasi-static tests and dynamic tests. Due to time reasons, I will put the focus now on the dynamic cell tests. We had different masses and velocities. The target always was to get enough kinetic energy to reach short circuit at every test. You can see here the test results. We have in black we have the 2.5 meter per second test. In blue we have the 3.5 meter per second test. In red we have 2.4 meters per second, sorry, with evacuated cells, so no electrolyte inside, and we have the same configuration for quasi-static here in magenta. What does this curve say us? If we increase the loading speed, the cell will get stiffer on the beginning of the deformation. You can see that here, and we will have a clear and higher first peak. To be honest, we are not completely sure where this first peak comes from, and we also have earlier short circuit in terms of displacement with higher loadings. Also interesting, the absence of electrolyte results in less peak here, or less plateau after this first peak. And as the deformation proceeds up here, we are very stiff compared to the same configuration in black with electrolyte, and we have we have the same stiffness here than or the same slope as in the quasi-static test. Now we come to thermal runaway testing of the cell. We did all in all 6 tests with the cell. We used different thermal runaway initiation, over temperature by heat bed at 4 tests, and nail penetration with 2 tests. There was no mean difference in the test results, so all tests are very similar. The maximum average cell temperature was 570 degrees over all tests, and we had in average 4.3 mole of vent gas released from this cell. Now we come to mechanical stack testing. So we did quasi-static and dynamic stack tests. I will go right to the results. The results are from the phenomenon very similar to the ones with the cell, but there's a big difference to the cell tests compared to the cell. To the single cell test, the maximum force and the displacement is much higher, which means that the stack improves the strength and energy absorption compared to a single a single cell, which is very positive. And we also try to reach a short circuit here at the quasi-static test. You can see here we managed with the maximum force of the test bench that we got a short circuit in the first cell. In the dynamic case here and here the voltage, we didn't manage to get a short circuit due to the mechanical loading, which is somehow sad for the test result, because it was planned to get a short circuit, but in terms of safety, it's quite a good result. Then we come to my last slide, thermal runaway testing of the cell stack. We did till now 2 different test configurations. This was the second one. The first one we had to improve in terms of cooling. We didn't have enough cooling power in the first test, so it was not a realistic situation compared to the battery pack itself. But the second test with the improved immersive cooling and spray cooling. You can see it here. Here is oil on the bottom of the box, and those are the sprays which cool the batteries. We had 3 cells here, and we sent the first cell into thermal runaway via nail penetration, and the result was very good. We only had 1 cell in thermal runaway. You can see it here. It's with the open vent. It's nice. The cooling oil spray washed everything away from the thermal runaway, so it looks quite clean. And you can see on the other cells are still healthy and were still working. And the highest temperature on the next cell was 190 degrees at maximum. So it's a very optimistic and very good result. And we are planning in Liberty to verify this result by another test with larger setup, which will be still this year in December. Okay, thank you for now. I will pass the word to Nick.
Thank you, Christoph. And Nick, we have like around 5 minutes. That will be okay. Great, thank you.
That will be okay. So thank you very much, Christoph. So good morning, everyone. I'm going to tell you a little bit more about the performance testing that we do. So you can go to the next slide, Christoph. So on this slide, I've shown an overview of all the tests we do. So we do the test at different levels. So at cell level, we did the characterization test of the cells. And now we are executing the accelerated lifetime tests. for which I'm going to show a bit more details on the upcoming slides. We also do cycling and performance tests on cell stack level. And we also do testing at system, so at battery pack level. That's then mainly focused on the performance testing. So on the next slide. So with respect to electrical characterization, we execute there the traditional characterization tests, so capacity testing, OCV versus SOC, HPPC, and also some fast charging tests. The main results of those tests serve as input for the theoretical cell model and also the development of the SOX algorithms of the BMS. With respect to thermal characterization, we focused on thermal conductivity tests, and also there they serve as the input for the cell model, but also as input for the development of the thermal management system. Next slide, please. So with respect to the accelerated lifetime tests, so the first type of test are the cycling tests. So there we are using different variables, so the charging rate, the mid-SOC, and also the depth of discharge and the temperature. We also defined and executing periodic checkups based on the number of full equivalent cycles that the cell has done. And these are divided in short checkups, but also more detailed checkups. And with respect to the evaluation of the aging process, we do this based on the capacity decay of the cell relatively towards 100%. And the same we do for the internal resistance. So we use two evaluation criteria to evaluate the current aging process. So on this slide, you also have a quick view of the test matrix that we are doing within Liberty. Then on the next slide, I've shown the test matrix for the calendar life. So there we're only focusing on varying the temperature and the state of charge. And with respect to the temperature, we change that each month according to a certain temperature profile. So you can see that we have two temperature profiles. So one with a cold climate and one with a hot climate. Also there we do regular checkups, and the aging evaluation is done at the same way as we do it for cycle life. Then on the next slide, I've shown the third cycling test, which is validation profiles. So they include realistic driving profiles, where some of them also include fast charging. And for example, the realistic one consists of regular commuting to work profiles combined with weekend trips, where we do slow charging during the night and fast charging during the day. We have also a variant where we have no pulses, so which is an accelerated version. And we have also the same test, but then without fast charging to see what the impact of fast charging is on the cell aging. With respect to checkups and aging evaluation, we are following there the same process. And also with respect to the climates, we also follow there the cold climate and the hot climate. So next slide, please. So with respect to cell stack testing, we have done cycling tests to focus on fast charging performance, but also the development of the thermal management system. So you can see the cycle that we did and also the logged temperatures. And until now, these tests will be repeated on the final cell stacks, which will be used in the battery pack. And there we want to focus on the optimal nozzle configuration for the cooling system. And in the second stage, we will also do the lifetime tests, the same as you do on cell level, on cell stack level, in order to extrapolate the results such that we can make a lifetime model of the complete battery system, since we will not do aging tests on the battery system itself. So next slide, please. So with respect to system level testing, we are defining in Liberty a detailed battery system test plan, where we include several topics. So we will include functional testing. So this means that all the measurement and safety functions of the battery pack are operational before it goes to the test bench testing. Then there is performance testing, which consists of acceleration profiles, regenerative braking profiles. There is safety testing, as Christophe already mentioned, but then in a simulation environment. And we will also do some vehicle level testing to check the drivability of the vehicle with the battery pack. And we are describing all the test descriptions in detail, such as the test objective, the start criteria of the battery pack, how the test sequence needs to be done, but also very important what the validation criteria are, such that we can objectively evaluate the performance of the battery system, and also linking the project KPIs to these. Then on the next slide. So this was my final slide. So on this slide, you can find the contact details of myself and also my colleague, Christophe. So if you have any questions, please don't hesitate to get in touch. So I want to thank you very much for your attention.
Great, thank you very much, Nick and Christophe. Okay, now it's time to move to HELIOS project, with Carlos Giebert from Karlsruhe Institute of Technology. Dr. Carlos Giebert earned his diploma degree and also the PhD in physics from the Saarland University, Saarbrücke in Germany. And in 2002, he joined KIT. He's currently the leader of the group for batteries, calorimetry, and safety, and his research is focused on the field of electrochemical, thermal, and safety characterization of lithium-ion cells. He's the leader of the cell testing in HELIOS project, so he will talk about cell testing in this project. Thank you very much, Carlos, for joining the meeting, and the floor is yours. You need to you are muted. Okay, great. Now, thank you.
Thank you very much for this nice introduction. It's my pleasure to present you today the cell testing in the HELIOS project. Can you see my slides?
Yes, we can see that full screen,
okay.
So that's great. Perfect.
Okay, so it's about the cell testing in HELIOS for parameterization of digital twins. So HELIOS means high performance modular battery packs for sustainable urban electromobility services. And the project coordinator is Professor Cornelio Barbu from the Aarhus University, and we are 18 consortium partners from 8 countries. So what are the general project objectives? We want to develop a new concept of smart, modular, and scalable battery pack for a wide range of electric vehicles. So we have 2 prototypes, this IMEV at the Aarhus University and this electric bus from the company Busonkaya, which is one of the project partners. And we want to improve the performance, the energy density, the safety, the lifetime, and the levelized cost of storage. We want to optimize the EV charge, including fast charging and discharge procedures and predictive maintenance schedules. And we want to create new designs and processes for easy of battery reuse in second life and recycling at the end of life, which contributes, of course, to the circular economy. And the main interesting fact is that we have both high energy and high power cells in our battery packs, and that we are doing different configuration depending on the type of car, bus, or anything else. So the main building blocks are here, of course, the battery testing, here the circular design of battery packs. Then we are developing the hybrid thermal management system, which is, of course, also a challenge because high power and high energy cells have different requirements for the cooling, of course. Then we have the battery management system with active cell balancing. We have an Internet of Things platform where then the digital twin is running with graphical user interface. We have a fleet management platform. We have we are also developing a charging system, and we are developing the power converters, which are also needed for the battery packs, of course. And here we have the life cycle assessment to optimize the circular processes. So the key objectives of the cell testing are, of course, to determine the coupled electrochemical, thermal, and safety data, which are either as required input parameters for the modeling needed or as the validation data for the simulation results. And we want to elucidate the aging processes by cyclic and calendaric aging study. So we have here the electrochemical and thermal characterization. We are, of course, doing different cycling tests, either in the temperature chambers or also in an accelerating rate calorimeter, both for the high energy and the high power cells. We are doing safety testing in accelerating rate calorimeters on cell level, electrical abuse, mechanical abuse tests. And we have matrices for the cyclic aging and the of the high energy and the high power cells, and of course also of the calendaric aging. In this case, we see that it was quite difficult to get cells from the manufacturer. So we got first cells from manufacturer, 40 cells, where we could start some tests, but then it took until month 24 until we received enough cells to start the aging tests. So we had to make significant changes to the aging metrics to optimize also the use of the resources within the time left in the project. And then we decided to do a design of experiment approach, which is shown here. So the matrix for the calendaric aging is reduced by looking for the correlation of the different parameters. So in this case, temperature and SOC, and doing some kind of sensitivity analysis, which parameters are most important in which regions. And then we were able to reduce the matrix from 38 to 19 tests only. Then for the pouch cells, we saw that we had some problems with the fixture design for the cell testing. So first we started here with the cell and the foams which had been proposed by the cell manufacturer, and then we found out that the temperature is too much increasing on the surface of the cells if we are using like rates of 2.5 C, which is allowed from the specification of the cells. So we decided to put the heat sink on one side and only the foam on one side, and then we saw that it was much faster, that the temperature went down again after such charging at high temperatures. So with this setup, we then started the cyclic aging tests, and the similar setup will also then be used in the final battery pack. So here we see then the temperatures on the different places here on the foam side and on the heat sink, which is made from aluminium. So for the electrochemical and thermal characterization, we did all these kinds of measurements with the different tools that we have here available, like the calorimeters, thermal imagers, heat flux sensors, and we were investigating normal conditions and different other conditions, also adiabatic operations in the accelerated rate calorimeter, which is a kind of worst case scenario, because then the cell cannot transfer heat to the surroundings. So this would mean that the thermal management would not work under such conditions. And all this goes then into the simulations of the thermal model. Similar for the electrochemical, this goes into the equivalent circuit model. For the safety testing, we have a whole portfolio of calorimeters at my institute, so we can investigate from components level up to 75 ampere-hour cells in our different calorimeters, and there we are doing then safety tests. And for example, one interesting finding was that if we are measuring investigating this thermal runaway experiments in the calorimeter with cells without this fixture, then the cells went to thermal runaway like 20, 30 degrees earlier. So this is also important to consider, that you always have to compare cells which are freestanding with cells that are in a setup that is also then later used in the application in the battery pack. Then we have here the ZSW, where we are measuring the released thermal runaway energy in an autoclave and also are doing then gas analysis. Then we have the typical crash test device. At the Danish Technical Institute, they have set up a nail penetration system together with gas analysis. So in this case, for example, we see here that for all SOCs that are higher than 0%, we see that we have a significant concentration of hydrogen when this nail penetration is leading to different reactions in the cell and gas formation. So for the safety testing, I have basically shown the main things here already. So we have here the heat rate seek test in the auxiliary rate calorimeter. We have the autoclave. We can do the standard thermal abuse and mechanical abuse and electrical abuse. And also this goes then into a simulation also of the thermal propagation modeling. Then we have battery test, a database, a data warehouse where all the different data of the different testing partners are stored. So this is just an overview how this would like. If you then add a new data set, then you will put here the different type of test and which equipment you use, so that everything here, also all metadata are available later. And then this can be used by those who are developing then the digital twin to put everything together. So for the different tasks, we have here the cell and battery pack testing task. Then we have here the battery modeling, where we have electric, electrochemical, thermal, and aging modeling. Then we are doing algorithms for the state estimation, so state of charge and state of health estimation. We are doing safety measurement and safety management in simulation. And finally, in the last task, there is the development of the complete model for the digital twin. So this digital twin then integrates all these different submodels, so the electric, thermal runaway, and aging modeling, and also then the different methods for state estimation, health measurement, and remaining useful life estimation into one complete digital twin mega model, which is then operated on this Internet of Things platform. So this is still in the development phase, because at the moment the different submodels are not finally finished. So this was an overview of the cell testing. I regret a bit that I couldn't show much results, but this is due to the restrictions of the NDA with the cell with the cell manufacturer.
Supplier. Okay.
Yes.
Okay, great. No problem, Carlos. It was very interesting. Thank you very much for the presentation. Now the third project, as commented previously, is MARBEL. Daniel Koch is the work package leader for testing in MARBEL project. We know well after these 3 years of research and innovation, Daniel Koch received his Master of Engineering degree in the electrical engineering for mobile systems from the Technische Hochschule in Ingolstadt in Germany. And since 2019, he has been working as a research associate at the Charisma Institute of Electric, Connected and Secure Mobility. Okay, his research is focused on lithium-ion cell and battery systems modeling. Okay. Well, Daniel, welcome. Nice to see you again.
Hello, good morning. Thank you.
And the floor is yours. Okay, we have like around 10 minutes.
Thank you very much.
Thank you.
I'll just try to share my screen. Just a second. So let me switch the screen. Now you should see it, I hope. Okay, perfect. Thank you very much for introducing Eduard, and welcome everyone from my side as well. I'm happy to introduce you a bit to the testing activities in the MARBEL project. And first of all, I'd like to explain a bit why I chose the topic name Against All Odds, Cell Testing Activities in MARBEL and Modeling Approaches. Well, in this presentation, I'd like to show you a bit, or give you a bit of a glance of the path of suffering, I would say, we went through in our project, which means we had some struggles to cope with getting the cells, starting the cell testing activities, and yeah, then in the end also had to change the cell manufacturer due to some difficulties. So I don't want to go through all of these points mentioned here. You can read them later as well if you get the presentations. Then first of all, we had the struggle in the beginning of the project to get the cells even. So we ordered the cell around summer 2021, and then after some endless or seemingly endless negotiations with the manufacturer, we ended up in January 2022 already to ask for an update with the cell manufacturer where the cells were and what the current status is. So for now, I'd like to just tell you we almost spent 1 year in negotiating with the manufacturer to get the cells. And for now, let's keep it as to be continued. So in the meantime, we tried to develop our I would say, design and have more details in our testing strategy we'd like to follow in MARBEL. So that means we were building our main concept around the including the AI approaches in terms of test data processing, as well as a support from the AI sector, which we have in the project with colleagues from Greece, to support the testing and the design of the tests. So what we had as main goals in the MARBEL project, and which we are following now, is that we not only want to validate and benchmark the system performance and safety, but also derive some innovative test procedures in terms of reducing future efforts in testing, and also validate a scalability of test results, especially when it comes to mechanical tests, like the other project colleagues said, mechanical crush tests or housing tests of the structure. We are trying to investigate the scalability of test results, since we are trying to have mechanical tests with a small scale housing, not the full scale. On one hand, to reduce the cost mainly, which would be caused by a full scale test, but on the other hand, also to validate the scalability in general. And then what we tried in the beginning of the project, due to the struggle with the manufacturer, we tried to include on one hand public data sources to train the AI models from the very beginning. On the other hand, we also included the requirements into the AI processing and the defined goals we had in the beginning of the project. And now, as an overall structure of testing, we feedback all the test results we have at a reduced scale, at cell level, and also at full scale later on in the project next year, to validate the improvements the AI sector can bring. I will show on the next slide what that means in more detail. As one thing to mention here is also this electric vehicle in the loop test bench. So we are not integrating the MARBEL battery pack into a common vehicle on the market. So we are trying to validate it in a test bench-like scenario, which we called EVIL, to get rid of the constraint of car dimensions and having to integrate it mechanically into a common vehicle. So in terms of including AI in the testing, we were thinking that it might make sense, which is also one of the, I can show already, so it's one of the topics we discussed in the COLLABAT cluster, to include like a collection of information, like also meta information about the cells conducted in a certain project. So what we thought is we determine all the necessary information to characterize a test in terms of intention of the test or expected result, also previous or subsequent tests, which can differ whether you have a mechanical abusive test or in general an abusive test or a performance test. And then the next step is to define some cost factors or efficiency factors to be optimized in terms of deducing new test procedures or selecting a certain test procedure. As an example, as Carlos just mentioned, with this design of experiment approach, to reduce also the tests necessary to get a certain result. So that is the overall approach. On one hand, having a data-driven cell model, which is fed by the data we get along the way. Then we have an equivalent circuit model, and we compare both of the models together with public data that are also fed into the data-driven cell model. And then in the end, we input to this AI processing method the cost factor or efficiency factor of a certain test and the desired results, and we hope to get some optimized test sequences, or at least test scenarios that can help to have a more efficient testing in the future. And here also mentioned on this slide are the mini battery pack housing tests. So that will be one thing as a test scale reduction, where we are trying to scale the mechanical test results to the real size housing, which is indeed not straightforward, but at the moment we are defining the necessary test results, also with a feedback loop of the cell of the housing simulation to know how we can design the test scenarios. Well, now if you might think, well, in the meantime, what happened with the cells? In the beginning of 2022, we got the cells finally, first cells for testing. So not the main order was placed at that time, because we already negotiated in the beginning to have 2 batches of deliveries of cells, just not to have to store them too long while we were testing. So therefore, we got the first cells. And then the next struggle was to contact the cells. So, which is also an important point. Maybe we'll talk in a bit more detail later on as well. We tried first to laser weld rectangular blocks to simply attach test bench cables. But since we were targeting a very high current, we also needed very massive cables attached to the cells. And in this case, as you can see here in this picture, it was just not stable enough, mechanically stable enough to account for the high forces occurring due to the cables. So therefore, we were thinking about a more mechanically stabler setup, or a more sophisticated one, which came up as also the one currently in use. We had sliced holes in a milled aluminum plate and just laser welded those to the taps. And another important advantage of this solution was also that we had a higher current carrying surface compared to these 4 laser welded seams with a rectangular solution. So this is now the current solution we have: laser welded L-shaped taps to attach the test bench cables, and also in the setup for the cooling rails, which I'll show in a minute. So then, after getting the cells, we started off with cell testing, just as regular, I would say. We started with formation cycles and then the characterization at different temperatures to get input data for the cell models. On one hand, for the AI data-driven models, and on the other hand, for the equivalent circuit cell model. And then, in addition, we had a continuous cycling to have some aging data or degradation data of the cells. And as a second batch, we had a continuous ultra-fast charging cycles. Now, since we were, one of the results was in the ultra-fast charging tests that the cells aged way faster than we expected them, we had to adapt a bit our ultra-fast charging strategy, which meant the continuous cycles were then replaced not by the ultra-fast charging 5 to 80% and down to 5, but with WLTC cycles. So now, if you might think, well, now that it's time to order the second batch of cells at the manufacturers, the problem was the manufacturer said, no, we're not going to deliver the big batch of cells. So, we had the problem that we won't get the real cells for building the packs and the modules as planned based on the test we had. So that meant we had to change our strategy and also switch the cells used in the MARBEL project, which meant we had to cancel out a lot of things due to cell time delay and also an overall delay in the project's time frame. So then we decided to cut up a few of the tests at cell level out and concentrate more on at module and pack level later when they are assembled. And on the other hand, as mentioned, we adapted our ultra-fast charging strategy to a WLTC cycling combined strategy, which means we have a continuous cycling with close to the street WLTC cycles, and then we have interim ultra-fast charging cycles to evaluate the performance of the cells in these phases. On the other hand, we left most of the parts of the cell testing strategy One of the good things we can say was that we got some information from the new cell manufacturer, so we didn't have to replace all the cells with a previous manufacturer, but we could keep some of the results, which are also now, I hinted it here, as an input for the AI models, just as training data to be replaced by the new data as they approach. Now, what else have we done so far? So to get a bit towards the model structure, we build up a concept cooling setup with 2 parallel cells and with a concept cooling setup, which we in general are using in the same structure in the later modules. So you can see them here, 2 top cooling rails and a bottom cooling plate connected to the cells. And here you can see the inlet with a bottom cooling plate and the outlet, which goes through the top cooling rails, which are also connected to the just showed L-shaped welded tabs to get rid of the heat. So in this case, we are investigating the thermal behavior of the cells as in a module-like structure. And on the other hand, we have a force sensor as well attached to this cell compound to know about the force evolution as the cells age, because this setup is mainly used for the continuous WLTC cycling test to get the degradation data and also the evolution of the force in a module-like structure. Now, this is just a quick overview of how the cell stack is built. So we have compression pads and thermal pads in between the cells, and these cooling fins that are connected to the top and the bottom to the coolant plates. On the other hand, we also have thermal measurements done with the cells, so to get the information about thermal conductivity and thermal capacity, mainly as an input for the thermal model, but also as a validation of assumptions we used to make a virtual model of the battery modules. Now, what is still planned? As I said, we have, since we changed the cells with a new manufacturer, we had a few information from the manufacturer's test reports. So we will mainly focus the abusive test procedures more on the module and pack level. So we have, as the other project said, a deep discharge, thermal runaway, overcharge, short circuit to investigate the behavior in the module structure mainly. And on the other hand, we might also have probably a vibration test at pack level. And as I mentioned before, the mini battery pack housings, only the housings with dummy cells, so no active cell mass is included, to investigate the crush behavior of the housing structure. And as mentioned before, the evil test bench is just a setup of 2 separated parts. We have an e-motor test bench and the MARBEL battery, which not necessarily have to be in the same place, but then can be tested independently in a vehicle-like structure, but not included in a real vehicle with the mechanical constraints. And last slide to finish off. I know I have 3 minutes more. We have some modeling activities, which I showed mainly before. We have the equivalent circuit model, which is mainly fed from the testing with the characterization tests and the pulse profile tests. And on the other hand, we have a data-driven model, which is mainly fed by the continuous cycling data. And we compare both in terms of performance and also what interfaces could be derived for parameterizing the other model mainly. And in addition, we have a thermal modeling, which is mainly fed by the data we got from the thermal characterization and the concept cooling test setup. So that is mainly the testing activities we have in the MARBEL project. And thank you very much for your attendance.
Great. Thank you, Daniel, for this presentation. Okay, we are now moving to the last project, and then after this we will have the roundtable to discuss with the different speakers. Okay, this last presentation will be presented by Bjorn van den Ven from Clintron and Chris Allen, both from TWI, both participants and working in the ALBATROSS project. Okay, Bjorn van den Ven is an applied battery scientist at Clintron Cleantech Batteries, and his role is responsible for leading research project focused on development of advanced battery estimation software and novel battery concepts. Okay, he also is a part-time researcher at Eindhoven University of Technology. Chris Allen studied material science at Cambridge and then did a doctorate in aluminium alloys at Oxford. After working as a research associate and also in a metals producer industry chorus in the Netherlands, Chris joined TWI Since for the last 20 years, he has been doing research on as a welding engineer, specializing in laser welding. Okay, Bjorn and Chris, the floor is yours. You can we can see the presentation full screen, so great, perfect. Thank you.
Okay, great. I'll kick us off. So in a quick summary of the ALBATROSS project is that we are focusing on improving the main goal is improving the peak energy density of the battery pack in the BMW i3, mainly through lightweighting and also through more efficient use of the battery capacity. Besides that, we want to achieve a reduction in charging time through better electronics, better monitoring, and better thermal management. And we want to improve lifetime of the battery pack. So with that, in this presentation, I'll go through the phases that we've had in big steps for cell testing, pack testing, and vehicle testing. So on the cell side, some of our partners have been working on test procedures for characterization of the cells. So we've measured open cell circuit voltages, capacities, some pulse tests, drive cycles, electroimpedance spectroscopy, also some thermal identification tests to be able to thermally model the cells. And these were all used for validation of the models that were made and the algorithms that are run in the BMS of the final battery pack. And besides this, we've also looked into the degradation of the cells. And I can show you here that we've done a bunch of tests on a subset of cells to see if the degradation was equivalent over time, or if there were any outliers. As you can see, the trends are showing to be relatively coherent. However, of course, the number of cycles and the amount of time is relatively short. Furthermore, our test data has also been used for development of an early warning battery failure detection software by Algolium. They have done lab testing to define the specifications of the cell, calibrate their algorithm, and find the thresholds. And they've also done real abuse tests, such as thermal runaway and penetration tests, to further characterize their algorithms. On the battery pack side, we have a suite of tests that we are going to run on the battery pack once that's finished at the first half of next year, hopefully, where we will be sooner starting on some small tests on a scaled module to test the sensing concepts, to validate if we can charge at the rates that we've designed, given the thermal systems that we've added. After that, we'll move to full-size pack performance validation, where we do some peak charging, some peak discharging, and validation of the full-size thermal system. Besides that, we'll do some pack lifetime validation. I'll add more on that in the next slide. And we'll have some second life testing, where we will take a pre-aged module from the other test and reconfigure it for using, for instance, energy storage. So for the lifetime validation, our partner Ceditech will perform battery pack cycling test in the second half of next year, where the vehicle battery will be simulated to cover around 48,000 kilometers, including some normal charging and intermittent fast charging between cycles at a certain rate. And these cycles can then be extrapolated to find if the real end of life of the battery is at 300,000 kilometers, as we have set out to achieve in the project, or if we need to, if we need to adjust our management of the battery pack during the life. And this will also help us to further check our theoretical models and calibrate our algorithms for the battery management. So finally, moving on to the vehicle, because once we put the battery in the vehicle, we want to validate that it's actually working. However, to start doing that, we've we've first done some baselining. So we have done a cycle of testing of the vehicle on a rolling road in a climate chamber, according to a European standard for drive cycling, including charging peaks at ambient temperatures and cold temperatures, and with different charging peaks. And this has given us a benchmark of the current battery that's in the BMW i3, and helps us to compare the battery that we are developing in the project. So as you can see, we've also used that to model the driveline of the vehicle in order to predict how our new battery will be performing. And we've achieved quite a good match between the rolling road and the computer model. So after the battery pack is installed in the vehicle, we'll repeat this rolling road assessment with more consecutive testing. And the goal here is really not to age the pack as far as we do in the standalone battery pack test, but to achieve achieve and test the functionalities in the vehicle, such as charging and discharging, to prove that the battery really works in the vehicle and fits in the vehicle. So now I'll hand over to Chris.
Thank you, Bjorn. So the final 4 slides of our presentation on the ALBATROSS just drill down into one very specific corner of the project, which does have some elements of testing and development within it as well, but slightly different perhaps to what you've been hearing from the other speakers. So next slide, please, Bjorn. So this final set of slides considers the joining together of the individual lithium-ion cells to make the modules and the packs, because of course that is an essential step in the production of any pack. And actually Daniel very nicely introduced the topic of laser welding in his talk, and that is one of a number of possible joining processes for fabricating arrays of cells into modules and packs. It's not the only one, but it is one that is often looked at by module and pack producers and developers, because it's a very fast, flexible, low heat input joining process. But one big question facing anybody wanting to move into this technological area is, well, which laser do I use? Because working with lasers and buying a new laser is a bit like trying to decide which new smartphone to buy or which computer. There is many different offerings in the marketplace, and none of them work in quite the same way. So I don't have time to go into the 4 key technologies which are state of the art in laser welding at the moment. I'm just going to go into 2 of those, which is the so-called CW single mode laser. So you can think of this as a garden hose pipe spraying a very concentrated jet of photons at materials to heat them up and to join them together, and the nanosecond pulsed laser, which is very similar, except that its energy comes out in the form of almost like a machine gun of bullets rather than a continuous spray of energy. Next slide, please, Bjorn. So the way that these 2 laser beams from these 2 different lasers interact with a variety of different materials that you might be interested in terms of bus bars and cell terminals, for example, so often forming an overlapping stack of 2 different materials. The way in which these laser beams will interact with those stacks depends on the material, of course, and also the characteristics of the laser beam. In this example, this is just showing you some scanned spiral-shaped welds that we've developed for joining together nickel-plated copper bus bars onto steel terminals of cells, cylindrical cells in this example, and a similar approach with the slight change in parameters for joining aluminium bus bars to steel cells. And I've just included at the bottom there a small amount of information on the electrical characteristics, the electrical resistances, which is one type of critical test that we're already doing at the coupon level on these different types of materials. And you can see there is something there called K. So we have a measure of the absolute resistance in milliohms, but also the relative resistance of these welds with respect to the resistances of the two parent materials that they're joining together. So an ideal weld would have a K of 1, and meaning that it is between the average resistances of the two other materials, and the higher K gets, the more resistive that particular joint is. So you can see there, for example, that the aluminium to steel joints are that little bit more relatively resistant than the copper to steel joints. And some of that is to do with the materials that are being used, but some of that is also to do with aluminium iron intermetallics, which form in that particular combination of materials, and that we don't get in the copper to steel joints. Next slide, please. So this is some similar information now from welds made using this machine gun-like or nanosecond pulsed laser. So it's a different type of laser. The welding parameters are quite different, but look at the welding speeds, and these are not a million miles away from the welding speeds that we can achieve using the other type of laser. So from a productivity point of view, these two types of lasers are competitive. And again, if you look at the electrical information at the bottom of the slide, you can see that once again, the aluminium to steel welds are, not surprisingly, that bit more resistive than the copper to steel welds in relative terms. Next slide, please. And another very basic test that I'm just going to mention to conclude the presentation is, other than the electrical properties, of course, the mechanical properties of these joints are important as well. We need to know that they are going to continue to remain joined together when the modules and packs are in use in the vehicle. And again, there's a lot I could say, but I'm very restricted on time. So you can just see the two graphs on the left-hand side are from the CW continuous energy output laser, and the two graphs on the right-hand side are from the machine gun-like or nanosecond pulsed laser. And the thing that I want to draw your attention to is that the aluminium to steel welds prematurely fail when joined together with that first kind of laser, whereas they are actually slightly stronger than the parent aluminium, the weaker of the two materials, in this when we're joining together that material combination using the second type of laser. So this is very much work in progress, but it's just to point out that the thermal histories of these welds are quite different as well. And that's important because some material combinations develop into metallics, others don't, but those that do, those intermetallics can be very brittle and have very serious effects on the mechanical strengths of the joints and lead to them breaking when then being used to put together a module or a pack. Okay, thank you, Bjorn. That's it from us.
Thank you, Bjorn and Chris, for these presentations and insights on the welding. Let's then conclude this first part of the webinar that were intended to present the different advances in the 4 projects. Okay, and we can move to the panel discussion. Okay, for this panel discussion, we will count with Professor Dr. Hans-Jörg Schweiger from the Technical Hochschule Institute, the university in Ingolstadt, Technische Hochschule Ingolstadt. The same institution where Daniel Koch from MARBEL project is doing research. Professor Hans-Jörg Schweiger received his diploma degree in chemistry from the University of Regensburg in Germany, where he also did his PhD in chemistry. Okay, after working in the automotive industry, he was appointed as a professor for automotive electronics and electric mobility in the Technische Hochschule Ingolstadt in Germany, where he is also a research professor for battery systems and head of the research group for safe electromobility. Okay, since 2020, he is also head of the Charisma Institute of Electric, Connected and Secure Mobility at the same university. Okay, so welcome, Professor. and welcome to this session. We can start with the roundtable then.
So thank you very much for your kind introduction, and maybe we can see the participants of the roundtable can join. So hope that we should be now 6, 7 people in the roundtable. I can see 1, 2, 3, 4. Not sure if everybody is here or switched online, but maybe we can start the roundtable. We see Christoph Breitfuß from the Liberty Project. He's working for virtual vehicle research. He's here. Yeah, welcome. Then we have Nick de B, also from the Liberty Project. He's working at Flanders Make. He's also with us. Then we have Carlos Siebert from the KAT and the HELIOS project. He's here as well. Great. Daniel Koch, my co-worker from the MARBEL project, is here. Very nice. And we have Chris Allen from TWI and also from the ALBATROSS project. He is here. And Björn van de Ven is not here, but we have one participant from the ALBATROSS project. Great. So roundtable is complete. So welcome here in our discussion. And we should discuss about testing and common points between the different project lessons learned at a cluster level, mostly focused on battery testing. And I'm working with batteries now since more than 20 years, and plenty of time I spent in my battery research field is testing, and we're still testing and continue testing the next whatever years. And what in my experience is, if you do tests, you will get a lot of results, and sometimes you're not so happy with results. There's some reasons why this is, and maybe we can find out why we sometimes are happy with test results, sometimes not. And what also would be interesting to find out the issues you have with testing, maybe on lab level or also on the organization level in the project. What can go wrong if you do battery testing, or what is good if you do battery testing, why you can have sometimes do tests, sometimes you cannot do tests, or why it's too difficult to do enough tests as you want. And also a big problem if you do battery tests, you generate a lot of data, and to find out how to use the data later on, so to make good use of this data. Yeah, so that's all the topics what I learned in the last more than 20 years regarding battery testing and what's difficult there. And based on this, we can do a discussion on the different topics. And maybe we start with the first question to the Liberty Project. So what are, from your point of view, the current challenges aging, performance, and safety testing of batteries? So that covers near the complete field of battery testing. Yeah.
I will, Nick, you are still muted, so I will start with safety testing, if this is okay. In safety testing, I would say there's a big difference between the abuse tests we all know, and it's not so complicated doing an abuse test than doing a real safety test which has the purpose for validation of safety measures on one hand directly during the test, and also doing the test for validation for virtual, so for model validation. And there's a big difference in that, and in terms of boundary conditions of the testing. You have to take much more things into account, and also for measurement data, it's much more than just saying the battery burns, explodes, or whatever. You need measurement data to have it for your models, and to learn something out of the tests, which is very challenging. And we learned a lot in Liberty Project, but we still have to learn a lot on that.
Maybe it's one question regarding your opinion. If it's are enough test specimen for abuse and safety tests? in a typical project that you can say it's enough, or that you have done enough tests, or just always lacking of test specimen?
It's always a compromise. I would to prefer to do more tests. I think we all agree with that here. But it's most of times difficult to convince everybody that we need more cells, and it's also a question of budget. So it's challenging, but this is why we at Liberty are doing also our hybrid approach with testing and simulation. It's challenging in the projects now, but for future it's a great opportunity for innovation and bringing simulation supported testing further and bring that to a level that it's applicable in standard develop or in series development of batteries.
Good. And I also like that you say that's the difference between safety tests and abuse tests, because it's very easy to burn down every battery. You just need enough fuel.
It's true.
That's very good too, because to ensure that something is safe is something completely different to make it burn.
It's true.
Yeah, that's absolutely true. And maybe regarding aging and performance, what's your comment about this?
So with respect to aging and performance, you have some traditional issues which you can always encounter, let's say. So first of all, you need to define your test sequences such that they are as realistic as possible, preferably using drive cycles. Another aspect, especially in aging, is the long testing time that you typically need to fully age and characterize your cells. So that's why you need to have, let's say, a strong link with the modeling that you need to do in parallel. So as Christoph mentioned, we also had a hybrid approach within Liberty. But also there we see, not only in Liberty, but sometimes in general, also in other applications, that it's difficult to have a good theoretical model, like a digital twin of a cell that can also simulate all the electric and thermal effects. Another aspect that we do within Liberty is we do all our testing, or especially the cell testing, with different testing partners. So the benefit there is that you can spread, let's say, the risk of the testing activities, but on the other hand, it also implies that in case you have inconsistencies in the results, that sometimes the investigation why can be very different, because it can be infrastructure dependent, it can be protocol dependent, so there could be multiple reasons. As already mentioned here, the data management is also very important. So you can retrieve a lot of data from the cells, very detailed, with a very high logging rate, for example. But this data is not necessarily useful, let's say, or too extensive to train models sometimes. So you need to find also there a compromise. So that's why in Liberty we have defined the data management plan, where we use with a sort of like summary file, which is a more detailed part of some bigger log file that we use for our models. And also another aspect, but that comes also later in the webinar on board, is to have the cell data from the manufacturer on the same conditions as you are testing, such that you can compare the cell data that you have with the one from the manufacturer. So, for example, what we see in Liberty now, we see some results which seems inconsistent in our testing activities, which seems to be, say, weird. But since we don't receive the cell data from the manufacturer, it's for us, it's very hard to see if it's, or what the reason could be, if it's from our side or is it a cell property or not. So that are in short a bit, let's say, the typical difficulties that you have. Another difficulty that is possible is with respect to performance, in the sense that also electrification goes now beyond vehicles. So we also electrifying ships and more heavy duty applications. And also there, the power levels are increasing very rapidly. So with respect to test infrastructure, there also difficulties start to arise to have infrastructure that is suitable to test all these high performance applications and high energy applications. So that's in general a bit the difficulties or the challenges that I see in aging testing.
Good. So you see that we have big influence of battery modeling and digital twins towards testing to reduce the amount of testing. And that brings us very well to the next question. So maybe suitable for the HELIOS project. And what are the key parameters that should be considered in cell testing for effective digital twin modeling? So we can use testing data to make digital twins and then reduce maybe testing later on.
That's an interesting question, but I think in the HELIOS project we are not at the moment targeting the second approach that we are trying to use the digital twin to reduce the testing. But at the moment I think we need all the data that we are measuring to just set up the digital twin. So as I showed, we need the data to have a thermal model, electrical model, abuse and thermal propagation model, and all these models and different approaches have to be put together, and this is quite a big effort, both for the testing and the modeling development.
And what's on behalf the key parameters we should measure to get a good digital twin?
I think what is really important is the aging. So I think this could be something that would also improve later. Then if the aging model is really good, then I think this digital twin will help a lot later in the application than in the vehicle.
Good. Yeah. And if now we have developed these digital twins, and then we want to believe that they are right, so we have to validate them, ensure that we have good digital twins we can use and trust for further applications. And that's maybe fits very well to the Daniel Koch, because he spent a lot of effort in making digital twins. And what's on your behalf is, what are the challenges exist in validating models or digital twins against real-world performance?
Well, first of all, I would say the biggest challenge is to define how to measure the real world performance, knowing the fact that we have a limited equipment available, or limited test budget in that sense, and also limited test specimen. So I think a good example for that is the thermal management validation. For example, in the concept cooling setup I just showed in the presentation, we have the problem on one hand. We have a model that simulates somehow the structure, but on the other hand, if we'd like to validate it in the real world, we need to measure all the respective values, temperature, cell voltage, and so on. And especially for the temperature measurements, we have a lot of spots, but on the other hand, we have a restriction in accuracy of the sensors. And so the first question is, well, where can we set the sweet spot between the effort we invest in a certain setup to validate a model and the efforts we have to spend to get it as accurate as enough to have a sure or a safe result in the end for the validation. And on the other hand, we have the trade-off between time restriction and also cost restriction in that sense. So that's one of the main challenges to define what are the limitations in our setup and how far can we go in terms of the validation values, and where's the sweet spot to be placed to set up the results.
Good. And to do all these tests and to find the sweet spot, you need a strong collaboration between the industry, preparing cells, for example, also doing some tests, but mostly for the research institutes who do the test to speed this process up, to give enough cells to be tested. And it's maybe a good question for the ALBATROSS project. How can a collaboration between industry and research institutes foster pioneering cell testing initiatives?
Thanks for the question. So I can answer this from the research side, but having had to work with a number of automotive OEM companies on other projects. So unfortunately, I think sometimes the view that the public has of academic researchers of being in their ivory towers, as we would say in English, playing with their latest piece of equipment, which in my case would be a laser. Unfortunately, I think sometimes a lot of that is true. We're very excited about new technologies, and we don't really think about what the problems might be in trying to apply them in the real world. And that's when we come up against the hard face of reality. And we've definitely experienced that in a couple of projects that we've worked with at TWI. So we've been keen to push out new technologies to industrial partners. And then some of the problems that they have are completely unforeseen. Sometimes they are very simple problems in terms of fixturing together arrays of cells to suitable tolerances for the joining technology that we then want to use to join them together. So they can be very mundane topics, but of course they are key if the technology is going to be successful in industry. So it's good for the researchers to have that reality experience. And the flip side of that, of course, is that we try to push these new technologies out into industry to improve what industrial partners can do. Make things faster, make things of higher quality, make things with more quality assurance involved, and so on. So that's a little bit of a general answer, but that's how I would see it, I think.
And what can you say from your projects? What were the key lessons you learned from your testing activities?
Again, unfortunately, I can only really answer from what we've been doing on the very specific topic of joining. And I think we might come on to talk about our shared frustrations with manufacturers and suppliers of cells. We've heard that mentioned in a number of the talks this morning. And what we found is even when you get the cell from the supplier or the manufacturer, they don't necessarily tell you everything that you want to know about it. It might be that that information is proprietary. They want to keep that secret. It might be that they don't know because it's not important for them. They haven't bothered to look at that. So we've had a number of topics where we've had to, because there are no answers, we've had to find the answer out for ourselves. And again, that can be very simple things like, you know, how thick are the terminals of the cell? What are they made out of? Are they coated in anything? If so, what is that coating? How thick is it? Does it contain impurities or not? Are the cells resistant to corrosion in the different service environments or media that the cells are going to be used in? So fairly simple questions and often limited answers from the suppliers or the manufacturers.
That's a situation I know very well from the last years I working with batteries. You don't get much answers. And some years ago, I was very frustrated still while working in industry. And I asked my supervisor if I was able to rent the torture chamber from the Regensburg city hall to go with a visit with a cell manufacturer to try the devices, but I was not allowed to rent this torture chamber to get my answers. So that I wanted to do, but not possible anymore. So therefore, we have to find more civilized, more suitable and civilized ways to get our answers than using these things there. Yeah, so that's a very good way to go to the second part of our discussions, because on your experiences say that we are very, very dependent from the cell manufacturers and the data. And maybe we can find out some solutions how to deal with the uncertainties we have in such projects. So because we know that the problems, and sometimes if you don't make if we are not cell suppliers on our own, we have to find solutions to deal with this uncertainty. Maybe there's some ideas from the MARBEL, HELIOS, and the Liberty project. Maybe from the MARBEL project, we start
Yeah, I'd like to start because it's a real passionate topic now, or it developed as a passionate topic, because I think an important point to add here is it's sometimes I have or had the impression in terms of MARBEL project that the manufacturer, they are also trying to get data from the ones who buy the cells and somehow to enlarge their repository of experiences they have with their own products. So that's sometimes also an issue, which is very interesting, because on one hand, as mentioned, they don't know some information, or they haven't thought about that this might be of interest for any recipient of the cells, and then they say, well, yeah, before we just let's collect all the information from them who buy the cells as like a preliminary or a prerequisite for selling more cells, and then that's always it's also a delicate situation, I would say, because it might happen. Maybe it also happened with us that after sharing some of the results, they might see, well, we didn't consider that one point. Maybe it's not as performant as they wished them to be, their products, and then maybe then was one part of the decision not to sell any more cells. So that's somehow a trade-off also in the the relations with cell manufacturers, I would say.
So don't use the thumb screws too much.
Yeah.
Yeah, that's a good idea. Maybe some experience from the HELIOS project.
Well, in our case, we made an agreement with our cell manufacturers that they give us all that data that they have. So we got quite a extensive set of measurement data from them, and we also agreed that we will share our data with them. So I think this will be a win-win situation in the end for both.
Okay, good. And from the Liberty project?
But I mean, it took it like more than 1.5 years to get the NDA working.
Yeah.
Also reminds me to one comment we had with one cell supplier also 20 years ago. It was a regular topic in this meeting. He said, you will get your data sometime. Maybe you get your data sometimes. Said at least twice each meeting. But in this case, it took a half a year, then we got sometimes the data. So it worked. Yeah. And from point of view from the Liberty project?
Yeah, from Liberty, we see the same as we see that Carlos mentioned. So yeah, we also have agreements with the cell manufacturer, but yeah, that takes a long time. And even then, if you have the agreement, it's sometimes very hard to receive any data from them, electrical data or some mechanical data. So that are definitely big challenges that we encounter. Since we are also not, that they don't need us to have their data, of course. So that makes it not always very easy for us to execute our tests and to validate our results.
Okay, good. So then once we signed all the NDAs after years of discussion, we hopefully get some cells, and then we have to prepare them for tests. And maybe we can talk about how we prepare the cells for testing, which requirements they must meet, and what expectations do we have for preparation of the cells. Maybe Mr. Koch, you can answer these questions, please.
Yeah, well, in our case, it was the main problem was we literally had no information about the cells, so we didn't know how would they react in terms of any malfunction. So it was like a total a black box like device we had to prepare for testing, and then also for the welding, because we had no option to connect it to the test bench. It was also a critical thing to give these cells to the welding lab, not knowing either what could happen if they get too hot or how they would react, because the manufacturer didn't tell. The only thing we had was like one page of the main voltage levels and so on, which could have been easily measured out by ourselves. So it was not of much use for these preparations. So I think one of the main issues in our case was not knowing the cells, not getting any help or support by the manufacturer, and on the other hand, having in the back of our minds that we need to get as much data as possible to run the models. So that was a trade-off, I would say.
Okay, good. So now we have the tests here, cells here, cells prepared for the test. And now we should define what we test. So we have to set up the scope of the test, what will be tested and what will be assumed as outcome. Maybe we can answer the questions from the point of view from the Liberty project.
Yeah, so from the Liberty project, for aging and performance at least, yeah, there we started from the requirements that we have set to the battery pack. So there we already defined the performance targets that we need to have. And also with respect to aging, what the end of life definition is with respect to internal resistance and capacity. And then based on that, based also on the amount of cells that we could have from the manufacturer and also from the budget, of course. Based on that, we tried to make the cycling and calendar life test protocol and also try to define some realistic profiles and also try to spread the cells based on the most occurring conditions. So you want to have the conditions that can be present the most. You want to have the results there. So that's a bit the way how we try to manage the test itself with respect to aging and performance.
Good.
Maybe from safety side, we start with quasi-static tests. We know how we start with a standard setting in quasi-static testing, and then we can estimate the energy we need for dynamic testing in terms of deformation energy, and we recount that in kinetic energy then for the dynamic testing. And so we do not have the test matrix on the beginning on, so we have to adapt the matrix to the results we get, and always have to put some safety margin on if possible.
Good. Yeah,
I could also add something from safety testing.
Yeah.
So I think in our case, I mean, we are using these accelerating rate kilometers, and I think one advantage here is that you can discriminate between the different exothermic reactions that are going on until thermal runaway, and this is a large benefit in comparison to a normal hot box test, for example. So you get much more information there.
So it's important to do the right test to get the right results.
Yes, that's correct.
That's also what you can say in general, not only for safety tests, but for all other tests. It's important that you plan your tests right. That's the
yes.
And
what we also experience is, of course, quite a large scattering of data. So you need enough tests to be on the safe side.
Yeah, that's absolutely right. And that's also what my students say if they make a test plan. I always ask which questions you want to answer with your tests. And it's very common that they don't know the questions. So then I ask them why they go to the lab and want to do a test. So then it's also for research, it's always you have to define which questions you want to answer and then choose the right test and the right test setup to get results. That's very important, yeah.
But this is also if someone from industry is coming, that you have to tell them what is possible and what you really want to know. So also this takes time. If they come and just tell you we want to do arc testing, then you have to explain what exactly do you want to find out and the conditions and things like that.
That's absolutely true. And it's also not always very good to do just a test according to some standard because it's written in the standard. That's all common in industry. Yeah, you have to do this test according to standard. Yeah, we can do, then you get the results, but is that what you really need? That's all.
Sorry for interrupting. Since we have like 15 minutes of webinar, I propose you that we maybe move to a wrap up of the session, and we take some questions that we already get in the chat that I saw they are quite relevant and linked to what you have been discussing on, for instance, sharing data and other topics related to the test. So I propose to do a wrap up, and then we take a couple of questions from the audience that you can answer. Okay.
Thank you. What we have seen from our discussion, that is very difficult in some cases to get the right cells at the right time, and also get enough data from the cell supplier. So that's what we have seen. That testing is also not that easy, and you have to ask right questions to define the right test, to choose the right test setup. Then what we've also seen that in most cases we cannot do enough tests as we want, so to get the use of the scattered data. And what we also seen that, yeah, we have to do a lot of different tests, especially if we have to do aging tests, performance and safety tests. And all of this related is correlating, because performance changes with age and safety behavior changes with age. So you don't test one cell, you maybe test 10 cells in different aging states. And then you can have different temperatures and state of charge and so on. We have a very multi-level or multi-dimensional test problem. That's what the difficulties we have. And that therefore battery testing is so complicated, but therefore it's so interesting. Therefore we do it, and therefore we like to do it. And we like to use models, digital twins, and artificial intelligence methods to deal with this huge amount of data. It's maybe a good wrap up of our discussion. And good. Thanks for you for the discussions. And now we have some questions from the audience.
Yeah, now it's time to, well, we have a couple of questions that I see here in the chat, but it's also the occasion if you want to ask on live, so you can raise your, my messages to the audience, you can raise the hand, and then Marina will give you permission to open the camera and the micro, or just the micro, and make the question. Okay. The first, I start with the two questions I have in the chat. Okay. One was related when you were talking about this the limitation on the data we get from the cell manufacturer and the NDAs, etc. It's like it's the data we get from the manufacturer. What happens in the data we can share, publicly share, for instance? And the question was if it is planned to publicly share the test results of any of the projects, or, for instance, sharing between the 4 projects, building some kind of common database between the projects to share the data obtained in the different projects. How if this is foreseen, or how this, or is there any limitation, or I remember, for instance, Carlos from KIT and HELIOS project, he told us, I cannot share the data because agreements with the cell manufacturer. I don't know the others. Some of you want to, or even Carlos, to comment this, if there is any plan to publicly share this data.
So in our case, as I said, we are not allowed to publicly share the results from cell testing. We are only allowed to share the results from the application testing of the battery pack later, where we are using the cells. So this is written in the NDA. So this is, of course, some kind of problem, but it's better to have such an NDA and get the cells than to work without cells.
For sure.
True. If I may add some or one point here, since it's always a problem, and we encountered the same one with the NDAs and not being allowed to share any cell specific data, we were also discussing within COLLABAT how we could anyhow share some experiences at least, and therefore related to the common database question, we were deciding to make a collection of experiences and I would say descriptions of a certain test with the desired result and what happened during the test and the setup itself, just to have like a relation between the question that was asked in the beginning and the answers we got from a certain test. So without any details specifically to a certain cell type or manufacturer, but more like the way of doing or the know-how during the test. And that could then help also without having a conflict between an NDA or anything else to get at least an information about who has done a similar test for a certain question I'd like to answer, and how did their test setup look like? Because setting up a test setup might be one of the most time-consuming parts in the testing. So that would be one option to tackle.
And here it would be a good opportunity to offer some possibilities to share and publish such data, because if you don't publish details, cannot publish details, it's very difficult to submit something like this in a scientific journal because they will reject it. And there it would be maybe an opportunity to use this Open Europe platform for publications, where you are encouraged by the EC to publish data from your European research project, which is for free. And here it would be good if they would be open there, that we just publish results on this level, just to make Open Europe aware that we are not able to share every data, but to be able to share test procedures and this stuff. Would be beneficial for researchers that we can publish there, because otherwise it would be very difficult to publish somewhere.
Mm-hmm.
That's
okay.
Yes, for example, I found interesting the approach with the different temperatures in the different months for the aging test. This is something new to me, for example, which I found quite interesting.
Mm-hmm. Okay. Good. Yeah, I think that there is this limitation in the age, but we need to think maybe on other which data that, for instance, test procedures or maybe at system level, things that we can share that can help. Regarding this point of the temperature, for instance, we get a question concerning when testing the state of the battery, SOX, in real settings. So that means like a car parked in a parking facility with outside temperature, so ambient temperature. Is surrounding temperature data sufficient, usable or do we need need the information inside the battery pack? And this question was from Thomas Martinsen. If it is not clear, I would invite him to unmute and explain it. But this is what I get from the chat. Anyone wants to take that one? So is the surrounding temperature data sufficient or usable, or we need also information from the temperature inside the battery pack?
Maybe I can comment on this. Mm-hmm. So I would recommend also to know the temperature inside the battery pack and the temperature distribution in there, and maybe even temperature distribution inside the cell. But here you have to know, once again, you have to define the questions you want to answer. But in general, it would be good to have knowledge of what's going on inside the pack.
Mm-hmm. Okay. I get more questions. Remember that we can, in the tools of the Teams, there is the little hand to participate. That will we will see that you want to ask a question. So feel free to use this button and then ask your question, opening camera or micro, both. Okay. We have another question in the chat from Jedula. Well, a question concerning the battery modeling. Okay. The question says, can I get some information that what types of open source softwares are we using for battery modeling to estimate the state of health?
So in our case, we are using MATLAB.
Yeah,
okay.
Same here.
Okay. Okay, and if it's by giving different depth of discharge and different temperatures. Okay.
Yeah, if I may just have a counter question to that. Well, if the point is different depth of discharge and different temperature is more, I think it's more related to than aging modeling. So I would say it's then the main question how that aging model is set up in terms of if it's a model with discrete sets of parameters for a certain degradation state, or I would say, or if it's more like a continuous model. So yeah, both. We're trying both, but mainly having interim checkup tests to get the information in at a certain discrete step.
Okay. Okay, great. Thank you, Daniel, for this. And also the person who posed the question is giving you the thank you. Okay, someone else wants to take the advantage to ask any question to any of the speakers about the topics discussed today. Anyway, you know that you can find these projects on the website, also in LinkedIn and COLLABAT. LinkedIn, you can follow the projects there, follow the projects by the newsletters. As you see, the projects are arriving to the last year and getting their systems, modules, battery packs, systems on the testing phase. So results on the innovation that have been performed in all the terms of waste reduction, increased thermal management, reduction of charging time, increase the lifespan of the battery, etc. All this these projects will be getting these results on this last year. So next year will be probably a year where you will find other opportunities to join workshops related to this topic of testing or other topics like BMS, weight reduction, thermal management, etc., where you will see experts from the 4 projects providing info about the results we get on all the work done in these last 3-4 years. Okay, so I encourage you to follow the projects and be attentive on this. Well, if there's no more questions, I will just like to remind you about our next COLLABAT webinar, okay, that will take place on the 5th November, okay, also online.
May I pose a question?
Yeah, please. Go.
I would like to ask Chris so about the welding and the intermetallic phase. So maybe it would be interesting to do some thermodynamic modeling of these different intermetallic phases. If do you think that this would help?
So we have attempted that in the past, not within the ALBATROSS project, within another one. The problem with the model is that the model, of course, requires some physical parameters inputting into it, and often these intermetallics are difficult to produce in large quantities, for example. So it can be very difficult knowing with any degree of accuracy whatsoever what the values of those physical constants are to put into the model. But if you can make a reasonable estimate of what they are, then you can indeed have a model. And we have had one project before where we've used a model to predict the size of the intermetallics as a function of the thermal history as the weld solidifies and cools down. So it's possible, but it's not necessarily immediately very easy.
Yes.
Okay,
yeah, thanks for the question though. Yeah.
Thank you, Carlos and Chris. Okay, well, now we are already on 12 o'clock. Okay, so there is no just last minute question, I would suggest to close the meeting. Thank you very much especially for presenters, but also special thanks to all the audience and the people interested in this topic that have joined it and posed questions to keep the discussion going. Okay. Well, thank you very much for the participation and hope you have a nice rest of the day. Oh, okay, let's keep in touch for tackling these challenges in battery systems. Okay. Thank you very much.
Thank you. Have a nice day.
Thank you very
Bye.
much.
Bye.
Thank you very
Thank you.
much.
Bye.
Thank you. Bye-bye.
Thank you for moderation. Bye bye.